So I hope you guys all see my slides, but before we start, I would like to use the first 10 minutes to just warm up you guys and also to give you some housekeeping rules. First of all, please be aware that this event is being recorded and it will be shared on the ROADVIEW web page and also on different social media channels that we have. So in case you guys have any problem with that, in case you don't want to appear in any of those, please let us know. You can simply email to this address, or you can also let us know privately in the chat. No issue about that. The most important thing is about interacting between each other. So we have two boxes here. One is dedicated to chat, so we call chat box. The other one is specific for the Q&A part. So in case you have any technical issues, like you can't hear properly or the resolution is not good or any kind of technical issue, please use this box on the left, top left, and just contact us immediately. In case you have questions regarding those talks, please use the Q&A box. It could be anything about scientific or technical questions or non-technical questions about the talk. But note that these questions will not be posed to the speaker immediately. So we will have 15 minutes for each speaker, and then we'll have one common Q&A session for all the talks. So there's going to be no talk plus Q&A session, but only talks. Okay? So during the talks, you can pose your questions. The moderator will go through them, and depending on the time, we will do our best to visit all those questions at the very end of the webinar. So what is it about? So this is we are talking about a series of webinars on CCAM, featuring the participation of global experts in the field. We have expert speakers here. We are willing to have a series, so this is just the first one. Hopefully in upcoming months, we will have a follow-up webinar. So our ultimate aim here is to raise the awareness about connected automated mobility. And we would like to present those technical challenges that we are facing in the field. And also, we'd like to highlight those innovations that are coming with this ROADVIEW project that we are currently working with. Of course, it's going to be also useful for networking inside the CCAM partnership, because we know that many CCAM partners are also joining us here. And we would like to also advise on standardization and regularization required in the context of CCAM. When we talk about innovative solutions, there must be also regularization. So we have to visit those as well. We have to present the market applications of the ROADVIEW technologies. I will talk about that later. So if you want to stay in the loop, please subscribe to our newsletter and event reminder. Mario, our superhero today, is going to share the those required links in the chat. Please just get subscribed. Specifically talking about today's session, we will start right now. This is the first part of where I welcome you guys. We welcome and give a general introduction by myself. And then the first keynote speaker is Edward Griffith from NIST. He's going to be talking about adaptation, resilience, and robustness of CCAM solutions. And then we are going to continue with Ryan. Actually, we invited both Steve and Ryan, but Ryan kindly accepted to give the talk. So he's going to inform us about CCAM current and short-term off-road use cases. He will talk about two different off-road applications, I assume. And then Ali Peker from Adastec, he's going to be talking about the safety of CCAM when it comes to harsh weather conditions. And they have developed a super interesting bus, which is also functioning in bad weather conditions. So perfect match for us. And then I will be back again here to give you some highlights about what's ROADVIEW and what kind of solutions we have when it comes to robustness and reliable systems working under bad weather conditions. Once we are done with all those keynotes, we'll have a dedicated Q&A session that covers all those talks. Okay? Again, there's going to be no break in between. So now let me just use the next 3 minutes to introduce the speakers. Maybe I should start with myself. Again, my name is Eren Aksoy. I'm an associate professor at Halmstad University. This is a small city in the west coast of Sweden. I have been also working as a visiting scholar at Volvo GTT trucks and Zensac, which is a company producing perception solutions for autonomous vehicles. I got my PhD in math and computer science in University of Göttingen in Germany, and I also worked as a postdoctoral researcher at KIT in Germany. My background is computer vision, robotics, and AI. Dr. Edward Griffith, he is an associate director for cyber physical systems at the National Institute of Standards and Technology, NIST, in the US. He's also adjunct professor of medicine, Center for Molecular Medicine and Genetics in the US. He is holding a PhD in mathematics and electrical engineering at MIT. He is an expert in the fields of autonomous transportation and system safety and security. Ryan Lamb is also from the US, from Southwest Research Institute. He's an executive director of research and development team there. He's holding a bachelor, BS in electrical engineering and MS in management of technology at the University of Texas at San Antonio. His background is in robotics and AI. Dr. Ali Peker, he is the CEO at Adastec Corporation, and he was also, I think he is still maybe an assistant professor at one of the private universities in Turkey, Okan University, and he is holding a PhD in computer engineering from Bosporus University in Turkey. And his domains of interest are automated driving, information technology, location-based technologies, and AI. Lovely. We still have 1 minute, and I know that we are approaching to 50. It's good. So far, so good. If there is any question up to now, I can take. Otherwise, we will switch to the next session, the first session actually, and Mativat will be the chair in this next section. So Mativat, I'll stop sharing. Maybe we can start if you have any slides, or maybe we can start with Edward directly.
Yes, thank you, Eren. I don't have any slides, so Edward, you can start sharing your screen directly. And while Edward is doing that, let me introduce Edward again and give some background. So Dr. Edward Griffith, he is an associate director for cyber physical system at NIST, the National Institute of Standards and Technology in the US. To keep it short, he has had a long experience in both academia and industry at several places in the US, Europe, Asia, and South America. And more recently, he is leading the NIST Automated Driving System Safety Measurement Technical Working Group. And today he will talk a little bit about automated vehicle program at NIST. So with that, I hand it over directly to Edward.
Thanks, Mativat, and thanks to the organizers, the ROADVIEW team for the invitation, the opportunity to speak a little bit about the work that's going on at NIST, and I'll relate it directly towards the end to this whole problem of ROADVIEW, or the weather, and an automated or robotic vehicle's ability to cope with all the variations. So let me see. You can see the screen, correct?
Yes, correct.
Yes.
Okay. Good. So the automated vehicle program was begun by me when I left Fiat Chrysler as the chief scientist there and moved to NIST. You can see some of the names of the people. It's a much broader team now than when I began this program. It also has received both NIST and White House funding. So you might recognize some of these people. The laboratories are acronyms. CTL is the Communications Technology Lab, EL the Engineering, ITL Information Technology, MML Measurement Materials, and PML Physics Measurement Lab. So this is a broad set of people, and we held about 2 years ago a workshop with some 1,200 representatives of industry and academia and government to sort of hear what they wanted NIST to do after we had been tapped. You can see many of them here. I won't even try to read them, but from those voices from industry, we focused in on a few, and you'll get a little bit clearer view in just a second. Sensor measurement or characterization of performance of sensors, mitigation, standards for adversarial AI, roadway infrastructure. I'll go a little bit deeper into that because I think it directly relates to this weather issue. AV communications. I think at this point, very few people believe that the AVs will be able to deal with all of the things they're confronted with on the roadway on their own. And so comms or communications will play a critical role in providing that information. And then we instituted and stood up an interaction testbed. I'll try to give an idea of what an AV interaction really is. Most people talk about unexpected or emerging interactions, and that is the reality of automotive production. So I'll get into that as well. NIST expertise had to be clear, the impact, and then the need from industry, hence the workshop. The structure includes artificial intelligence, which I co-lead with the Information Technology Lab, safety, a simulation or co-simulation environment for preliminary assessment, cybersecurity, Diopter as a tool developed by NIST in order to give a dashboard to a simulation environment, traffic infrastructure, both hardware and software, teleoperation as an instance of communications for either remote driving or cooperative driving, perception itself. So that team I also co-lead, and I'll give you an idea of what they've done, and then the AV communications. So most recently, now in the month that's just passed, in September, from the 5th to the 8th, the second workshop was held. You can see some of the people that spoke there, again, partitioned into these groups: AI, infrastructure, cybersecurity, perception, and communications, ranging from experts in AI from MIT all the way to Jim Misner at Qualcomm, which is driving, in some sense, the CVDX basis for communications. I insisted on adding the infrastructure piece. There were 8 states in the US, including Arizona, California, Georgia, Massachusetts, Michigan, Ohio, Texas, Utah, and Virginia, that wanted to understand what they should purchase for infrastructure, what technologies that would complement the operation of AVs. So the program components: assessing automotive sensor performance, minimizing the risk in AI. There, we've developed on the team that I co-lead with the ITL group examples which show that more learning doesn't give better AI. And then in particular, we've introduced aleatoric and epistemic uncertainty into the YOLO vision program. Could have been done with any of them, so that displays the confidence level of the classification that's performed by AV vision. Monitoring of cybersecurity tools for measuring adversarial machine learning and defensive mitigations, evaluation of communications, and you'll see a concrete example there, and then complete vehicle behavior in this interaction testbed. Looks like ROADVIEW has bought the same car we bought. So it looked like a Ford Fusion. There's a lot of those out there. This one doesn't say Uber on the side like the one you can see here. So we transition from the characterization problem to an architecture for the co-simulation, and finally to the full vehicle testing. Experiment definition is basically following the lead that SAE has laid out. Events, I'll describe some of them. Most of them are pulled from SHARP2, which is the largest naturalistic driving database in the world, as far as I know. Choose an automation feature. This is now a technical term in the sense of SAE. So those features are classified by level of automation. Behaviors themselves are being evolved, but precise definition is to come. The operating conditions, NIST introduced the OES, which is the measurement science for the ODD. Not a lot of consensus on the ODD side as yet, but ultimately I expect it. And the OES is literally the measurement technique for each one of those parameters that describe dimensions. And then determine the sensing, AI, cybersecurity communications aspect or elements of the experiment, the configuration, and then finally configure and run those experiments. I'll give you a little bit of a closer look at the operating envelope specification. Here, it represents all of the precise information that's required to reason computationally about the AV's performance in its environment. So this would include many things, but among others, infrastructure, roadway width, lane size, lane marking location, and much, much more. Behavioral competency is the term used by SAE and the AVSC, the Automated Vehicle Safety Consortium at SAE. I'm not going to read this slide. Focus for a moment just on this formula you see in the middle. It's actually a formula in signal temporal logic. It can be compiled by the tools we've developed, and it's used to specify the behavioral competency. So if you're looking at one related to lane keeping, then you're going to see that velocity is kept below a max, and the distance from the center of the roadway is below a fixed parameter. So there's very little wandering. This then gets compiled and used during the simulation and the physical vehicle run in order to assess competency of the AV in that behavior. A little bit more about this. You can see the lane following spec in STL, as it's called. You can see as well a description of the time-related parameters. Again, I won't go into the details. I just wanted you to have a chance to see you can specify an AV behavior as part of a feature formally, and you can compile it into your program. So what are the methodological issues? There are many here. This is a technology that I wouldn't say is ready for prime time. What's the divide between simulation and physical testing? What injections interactions are of interest, are realizable in a cloud environment, so we don't all try to load impossibly on our laptop the simulation components, are realizable in physical testing. How can we use the cloud to share compute, and what can be migrated and in what way from the simulation environment to the physical vehicle? So an example, EEBL, or electronic emergency brake lights. Here, the simulation environment uses NS3, it's a network simulator, and the standards for those safety messages developed in SAE J2945 and elsewhere. And as you can see, the issue is a red car hard brakes or even stops in the roadway. The green car, RB2, is blocking perception for the host vehicle, the blue vehicle. And what happens during this process is The standardized communication messages are sent from the red car to everyone, but in particular to the host vehicle. And the experiment involves checking just how difficult it is and how much time it takes. Give you an example of the digital infrastructure for safety. Here's many of the things that those 10 states I mentioned are concerned about. Primarily intersections, it's a heavy hitter, but also zebra crossings, crosswalks, intersections of all kinds. People running across the street to catch a bus. This happens just about everywhere I've lived, including Sweden, Germany, France, Russia, a long time ago. So it's a problem we face, and the measurements that are needed and the collaboration between the digital infrastructure and the vehicle itself is absolutely essential, and I'll show you why. Some SAE standards related to those scenarios or use cases, perception status, and so on. And finally, AV performance measurement, which I've led that group. This is called a power law or an S-curve for obvious reasons. It advocates a measure in terms of information processed and embedded in the infrastructure for guiding the vehicle. Phases of AV operation, ranging from knowledge-based or heavy processing, reduced processing during a rule-based activity, and then finally skill-based behavior. What's being measured, what's being graphed is the information processing. And during that middle phase, which you can see, there's an opportunity, and we've done it for hundreds of years actually, embed structure in the world around us in order to make the work we do easier. In this case, digital infrastructure inherits those rules. Lane markings, signage, etc. are all physical embedding of information that help human drivers, and the same task will be faced by AVs. Thank you so much for your attention.
Thank you so much. Thank you, Edward. So we are exactly on time, and if you have any question, please use the Q&A box, and then I will compile them and ask Edward at the end of this whole seminar. With that, I hand it over to Graham.
Thanks, Matthew, and thanks, Dr. Griffo. So next up, we have Ryan Lamb, who's the Executive Director of R&D at the Southwest Research Institute. I won't give any more of a detailed introduction, Ryan, given that Aaron's already done it for you. I can see your slides are on the screen, so over to you.
Great, thanks, Graham. Can you hear me okay?
All good.
Okay, good deal. Well, thank you very much for the opportunity to talk to you today a little bit about a couple of off-road use cases. And so what I want to do is kind of extend upon what Edward was talking about relative to a testing methodology and talk specifically about a couple of off-road scenarios, a couple of off-road use cases where automated vehicle technology can be realized in the near term. First, a couple of slides to kind of give you a perspective of where I'm coming from. I'm located in Texas in the United States, and I work for a company called Southwest Research Institute, and our focus is on applied research and development. So we help different companies, we help different governments try to accelerate budding emerging technology that's showing up in academia and get that applied and into products that the consumers can use on a daily basis. And so what our company does is we're effectively a nonprofit in the US, and we develop, package, and transfer technology. So we're located in South Texas on about 1,500 acres. We do about 800 million in turnover a year. And for the last 20 years or so, we've been focused on automated driving, both on-road and off-road. And I think the off-road context is uniquely important here when we're talking about adverse weather conditions, because it can dramatically change the mobility of a given platform itself. And so some of the pictures you see here are just a snapshot of a few of the different platforms that that we've automated for a variety of different customers. One of the things that we like to do at the Institute is focus on areas where specialty operations are needed to be automated. It may involve custom platforms, and you'll see one of those in a minute. And then, of course, the part that's relevant to this webinar is the complex environment task. So jumping into the first use case that I want to talk about today is a smart agriculture application. And in the United States and elsewhere, it's very common to bale the cellulosic material, the grass, if you will, from different fields to feed livestock and what have you. And so in the United States, we're very fortunate that we have some very, very large fields. But what that means is that the baling application
Mario?
Yes, I think.
Yes, we lost Ryan, right?
Yes.
I think we lost Ryan. Yeah.
Okay. Should we give him a minute to rejoin Mario?
Yes,
Yeah.
to see if we can rejoin you.
Yeah. Okay.
Perhaps we should then move to the next presentation, and if he rejoins, then he can pick it up later.
Okay, then I can take the word. So the next conversation will be brought to you by Dr. Ali Peker. He's the Chief Executive Officer of Adastec Corp, which builds autonomous buses, and he is a pioneer at the industry. He's also assistant professor at Okan University, Turkey, and holds a PhD degree in computer engineering. The floor is yours.
Thank you very much. I will just start with what we are doing. At the end of the day, we are a startup and we need to solve a problem. So I'm coming from a huge city with 20 million people. The biggest problem is the congestion in traffic. So none of the current solutions, robotaxis, shared mobility, solves that problem, since they increase the utility in the roads, utilization in the roads, and the basic solution to these problems like congestion, carbon emissions, and driver shortage is the automated buses. To cover that, we introduced 28-feet bus, full electric, with Karsan, bus producer in Turkey. By the way, Turkey is the #1 country for production of buses in Europe. So most of the bus OEMs produces in Turkey, including MAN, Mercedes, and there are 4 or 5 very good OEMs who export these solutions. Our solution is a full electric targeted for in-city public transit operations. One of our differentiation is that we don't do retrofits. So we work with the OEMs and integrate our technology in the factory so that the solution can scale. So the bus comes out with our sensors and with our software out of the factory and goes through all standard tests and procedures and homologation procedures. And we are the only company offering this high capacity buses as a product. We made several deployments. I will give you some details about them. So first one was in Michigan, inside the Michigan State University campus, bringing students from outer parking lot to the center of the campus as an express service. The Michigan State University campus is huge. There's a lot of foot traffic, 7 intersections, some unprotected left turns, some and the roads are a little bit narrow compared to US standards. And in the US, it's allowed to turn left in the green and then turn right in the red. So there are different rules. And so we operated. I will show you that, you know, the weather is not nice as this always in Michigan. So I'll show you other samples. We also made other deployments to in the Europe. One of them is also a good example for this topic is in Stavanger. It's close to 2 years now and operating in public roads and integrated to public transit. And also there's a lot of foot traffic. Normally we are having a lot of rain, a lot of snow, and this is a touristic area. In the summertime, there is cruise ships coming in, blocking our GNSS reception, and plus pouring around 5,000 tourists who like to walk in the bus route. So at the end of the day, everybody's talking about adverse weather conditions, and then our team is more comfortable with heavy rain and heavy snow rather than having a lot of tourists looking their phones in front of the bus. So this is in operation. It's a paid operation, and we are extending our operations in Norway. Currently, we are testing in a longer route with higher speeds and a huge tunnel. There will be a segregated lane in Stavanger where we're going to deploy maybe more buses. And there's also roundabouts and unprotected intersections in this route. We are the first company who deployed a bus in Europe in public transit, a full-size bus, and we are the first company who deployed a full-size bus in the US. And now we will be deploying several other locations. One of them is in Germany. Next March, we will have a bus in Germany, Hanover, and we're going to deploy to Buffalo. And this time we will have an FMVSS Buy America ADA compliant bus, and it'll be our base model in the US. We are working with several other OEMs to be able to deploy. Currently, we are trying to also work with another Australian OEM who has a 40 feet footer. And we're going to deploy that to Sydney if it's concluded this month. And we also do some preliminary studies for Sweden, Arlanda Airport, and we are expecting for a funding. So we will be, if the funding is approved, we're going to deploy over there for between Arlanda Airport and a satellite city. We also deployed to Istanbul Technical University. Now we started operations over there. So if we come to our deployment in Michigan, the challenges were there's extreme cold, and which tests our sensors, and some of our sensors are not inside the bus. And those, especially extreme cold, creates a lot of exhaust fumes, which sometimes looks like a human shape or sometimes looks like a car. And then there's extreme heat in the summer, and there's heavy snow and heavy rain. And normally we had a infrastructure for communication with spot technology, signal phase and timing, but that technology didn't work at the beginning and sometimes sends wrong messages. So we need to find a way to fuse the communication information with the perception, since normally you expect the communication should be 100% reliable, but that was not the case. So we also tried to use the signal phase information to understand if the current message that we are receiving from the signal is wrong or right. And then so also the human response is generally a problem, since they are not aware of the bus. Sometimes they just stand on the crossway, and traffic rule says that if there's someone just stepped on the crosswalk, you need to stop. So you wait for them, they wait for you. So you need to devise the method of communication with them. And there's a lot of cyclists, scooters, jaywalking people, and there's a lot of traffic rule violations. People are passing you, cutting in front of you. Sometimes even while the bus is parked, especially some huge other bus drivers were very close. And also there's a lot of maintenance work going on the roads. And for example, in our Stavanger route, there's taxi drivers generally park in the bus stops. So you need to pass them or find a solution to that. And then we need to operate this bus and we need to get the NHTSA permit. And NHTSA permit, they give us a permit at the beginning and asked us to get some test result in closed areas, then allowed us to operate without passengers, provide them data, and then they allowed us to get passengers on board. So when it comes to adverse weather, first we started, for 5 years, we collected a lot of data in our route. These are scenes from our route. As you see, there's a lot of other buses. The road marks are not seen. And we are also operating at nighttime, so we are getting a lot of snow covering our cameras and LiDARs. And there are a lot of areas where there's no communication. So we collected a lot of data in those areas. That the advantage of being in Michigan and Norway allows you to collect this data. We determined our problems. As you see from this LiDAR scene, there's a lot of noise because of the snow. And then the exhausts are coming out. So, and then sometimes they seem like in camera, they don't look anything, but for LiDAR, they seem like the extension of the vehicle sometimes. And then the snow's sprayed in front of us because of the, even it's worse than the snow itself, the spray coming from the locations. And then there's a lot of particles coming out, which sticks to your LiDARs and cameras and avoids the perception. And then with the LiDARs, there's a lot of lumen effects. So somehow, especially, it's very difficult to, especially the reflective surfaces, when they became wet, they reflect laser in different types, and they create wall-like objects. And then sometimes you need to clean the sensors. So we also devised the methods for creating cleaning, cooling, and the sensors. So we have the good thing is in the bus you have a lot of pressurized weather, and then also you also have a lot of water. So but to be able to use electric efficiently, we created a method with our own motors. So we used different sensor modalities. So we fuse them. We use LiDAR, radar, RGB camera, and thermal camera. So thermal camera is not used in many places, and they work like a fault tolerant system. And currently, we also, in some longer buses, we have even 6 LiDARs. The good thing is we have a good position. A top LiDAR is not obscured by other cars, so we generally able to see the front. So the having other cars, and we have, since our LiDAR is on top and provides a good view, and it's a little bit extended, and we are able to use them as a fault tolerant system. So not just fuse them, and we are able to, and we trained and improved AI models. Generally, in our system, we have a fault tolerant, and we fuse the deterministic and probabilistic system, and we use them as a voting system. Since we are carrying people, we are not going too fast. We don't want that if we don't understand something, then we generally tend to slow down if we don't understand the scene. And then we did a lot of research projects with Michigan State University and University of Michigan to distinguish these objects. So normally we started in the safe matter. Our deterministic system were stopping when they don't understand what it is, and then we try to teach them. And these experiences caused a major achievement in our ODD in adverse weather conditions. As you see, we are operating in rain. This is from Stavanger. And we are now one of the few companies who can operate in heavy rain and moderate snow. And we improved the rider comfort, since sometimes because of sprays, our deterministic system kicks in and makes a break for non-existing objects. So that's why we removed those false positives. And also, we didn't just do technical improvement, we also did a lot of improvement for the riders, and we did a lot of collaborations to understand the requirements by especially people with disabilities. Our new bus model, that's why I have a automated lock, for example, since generally what we have seen is that disabled people hates those elevator type loading mechanisms. So they prefer ramps, automated ramps, and automated locks. They don't want any help when they are getting in. And also we put a lot of visual and audio content to help other disabled people and to be able to communicate with the pedestrians. So if you look at our extended ODD, we are able to handle many different things like speed bumps and on-the-way bus stops, heavy snow, uphill and downhill. And we are able to communicate with traffic light together with perception, so we can compare them. And we are able to operate in indoors and tunnels. We are currently operating in 800-meter tunnel in Norway. And we are able to operate with rain and jaywalking. This is an interesting scene. And sometimes bicycles go in front of you in crosswalks, so we are able to handle that. And unprotected left turns. And and also we are able to pass construction zones, take over them. And currently we are able to take over. And our next thing is some of the new things we are doing. This is platooning. Currently, this is from our test track in Istanbul. We are operating 2 buses to make with V2X so that we can have a platooning system. The good thing about bus platooning is that it doesn't require they need to be too close. What you can, the target for this kind of operation is more optimization. So instead of having a articulated vehicle, you can have 2 buses. And then when you don't need the trailer bus, you can use them separately. Most of the fleets, even though they have thousands of articulated buses, because of the energy concentration, they only use them 7% of the time, and they keep lying in the depots. Other than Metrobus lines or segregated lines, they are not used, and their turning radius is very bad. So that's why we started that. As I explained later on, another new thing is we're going to deploy a Buy America compliant bus in February to Michigan. So we are replacing the European bus in Michigan, and we're going to deploy the same bus to Buffalo in the US, and where we're going to hit even more snow. And we're working with future mobility strategy of Michigan State University. So we would like to upgrade to CV2X. And then we would like to communicate with emergency vehicles so that we can do the yielding use cases with them. And our HQ is in Ann Arbor. We have locations in Turkey as our R&D center and Helmond in Holland. And we are opening a new one in Hanover because of the Germany projects. So if you want to communicate with me or Adastec, you can have my email in the chat box. Thank you very much.
Thank you very much, Dr. Ali. I guess we can go on with the presentation that was left out. So I leave the word to Graham.
Yeah, thanks, Umit. Ryan, do we have you back?
Yep. I'm going to leave my
Excellent.
camera off though and hope for the best here.
No
I don't
worries.
know what
Yeah, this
happened.
is
My apologies. It was a network issue.
no problem. This was the slide you left us at, Ryan. So if you could start from this slide, that'd be great. Thank you.
Great, sure. So the problem at hand is basically to collect these round bales that are sprinkled around all over these large agriculture fields and stack them up next to the highway. And to do this operation at night is the goal, so that in the morning a freight hauler can come by and simply pick up the hay bales, load them onto a truck, and then transport them to market. The issue is the big trucks can't get to where the round bales are currently because they're spread out all over in the field. So this is a picture of the system that's developed by a U.S. agriculture manufacturer, Vermeer. So the mode of operation here is that the platform, the headless tractor, is needing to search for the bales in the field because their positions are not known, accurately detect the location of the bales, then navigate the platform and orient it in such a manner that it can pick up multiple of these bales. You can see in the picture here, there's 3 of them, and then transport them off to an unloading location. So here's a picture of the platform in operation. Some of the challenges here are in determining where the particular bales are because their orientation is not necessarily known. The platform then has to orient, and it has to handle any of the terrain peculiarities that might exist. The agriculture fields are not exactly flat. They look flat here, but sometimes it's operating in a muddy environment and things of that nature. The one good thing that a system like this and an off-road use case like this has going for it is that it's typically not in operation during very adverse weather like snow because the hay is baled during the growing season. And so usually in the wintertime, that's not necessary.
It's not Ryan's day today, I guess.
We've lost him again, haven't we? Give him a few
It is.
seconds see if he rejoins.
It's just Monday and he starts with that.
I think we can solve all the problems in automation and everything, but printers and showing videos will be a problem all the time.
Yeah, I'm guessing you guys don't have me, huh?
We have you, Ryan.
I think you're back. You're back.
You have
Ryan.
me? Can you
Lucky.
see this? Can you see the slides?
We can
Yeah.
if you put it back into presenter mode, please.
Okay, I'll do that. Good deal. All right, second use case, hopefully before my connection dies, is more on the defense use case side. And so we're going to talk a little bit about the importance of ground slope mapping to enable off-road mobility. And so the reason this is important is because automated vehicles operating in an off-road context need to avoid the slopes that could potentially flip the platform. Some are critical and they could potentially disable the platform permanently and prevent its autonomous mobility movement. In some cases, the path planners can utilize the slope data to plan more efficient paths. They can get to the destination quicker or faster if they have a sensed understanding of what the topology looks like. And then also from the standpoint of a defense application, the behaviors could be leveraging the topology in such a manner to provide a shelter or overwatch capability to obscure the location of the platform itself. So looking specifically at positive and negative slopes, these are some tests that we ran in sort of a mild off-road scenario on our campus here in Texas. And the video on the left-hand side is showing positive slopes. You can see the cost map there. It's not picking up the fence line or any of the vegetation. What it's picking up specifically is the slope itself. And so high slope areas are shown as dark red, and then lighter slopes in kind of that orange or pinkish color. And then on the right-hand side is more negative slopes. Again, this could potentially be a catastrophic movement for the automated platform. Using it in terms of path planning, you can see here there's a path that's projected or an endpoint location in blue or purple, I guess. And the system is utilizing the slope information, in this case a positive slope, to plan a traversable path to get back onto the road and then to continue to navigate. So this is very, very important from the standpoint of autonomous mobility from a defense context. And then just real quickly, hopefully I'm still with you. One of the things I would like to mention is that a lot of the off-road problems have been mostly solved. It is possible to use different sensing modalities that exist today to do material classification, to understand the natural environment. It's possible also to do object segmentation and to determine kind of natural environments, and then also to understand the terramechanics, the wheel to ground interactions, incorporating vehicle dynamics to potentially do some path planning from a topology standpoint. Areas that I think still need some solution, and this is one of the reasons we're interested in ROADVIEW, is obviously the adverse weather conditions, but also trying to understand what is going on underneath the snow surface from a mobility standpoint. Because if you have an off-road platform that's operating in those environments, it's not just important to understand what the snow surface looks like, but it's really important to understand what's going on below the snow surface forward of the vehicle. And then, of course, a common problem that off-road mobility has with on-road mobility is the frozen water problem, being able to detect black ice, things of that nature, and then trying to deal with that from the standpoint of high-speed mobility. And then the last one I threw out there is not necessarily adverse weather condition related, but it's more an area where I think there needs to be more research, which is in low gravity mobility for off-road exploration or off-world exploration. So with that, hopefully I'm still there with you guys, but that concludes my remarks.
Thank you, Ryan. Back over to you, Aaron, I believe.
Yeah, thank you. We still actually have time, Ryan. I agree. You thought maybe we were running out of time, but it doesn't matter. Just a short note, please, if you have any questions, just use this Q&A box on the top. Do not pose your questions in the chat, which is dedicated to technical issues. All right, with that, now it's my turn. I'm gonna briefly introduce the project ROADVIEW. Just give me a second. I'm just trying to see whether I've shared the right screen. I assume you guys see my full screen, right? Any feedback?
Yes,
Good.
we do.
Great, lovely. Okay, so today, many times you have heard about this word ROADVIEW. What does it mean? It means robust automated driving in extreme weather. This is a Horizon Europe project that is coordinated by Halmstad University, by myself. We have a budget of like almost 10 million euro, and we have like 15 different partners all over from Europe. So we are just dealing with these weather-related challenges, how to make autonomous vehicles more robust and reliable when it comes to such challenging cases. I'm pretty sure you have seen these fancy videos on YouTube, like many giant companies invest a lot of manpower and resources on implementing or making these vehicles available, working autonomously on road, particularly in clean weather. Actually, I should update those slides with the cool videos from Adastec, because apparently it looks like they also have solutions for snowy cases. But anyhow, so we know that those big companies, they collected tons of data, millions of data, to boost their learning system. But to be honest, not every kilometer driven is a crow. So again, most of those vehicles have been primarily trained and tested under very clean, optimal weather conditions with very clear visibility. Okay, the problem starts when we start talking about bad weather conditions. This is particularly important when we consider like the fact that 50% of the European population lives in regions with snow cover in winter. So it's a huge number, and this is a real challenge that we should be aware of. So the challenges start with these bad weather conditions cover different aspects because of having fog, rain, and snow, and it is affecting. There's a substantial effect on the functioning part of the perception units as well as the control units. So I will do my best to summarize those challenges first. So one of the challenges is the problems that you may face with the sensors. Sensors may get covered by snow, water drops, and mud, and this may cause some degradation in your measurement. And the noise level that you may have in your readings, in your sensor input, is unknown, right? It may change from weather type to weather type. So it's something that we have to handle. Of course, this will substantially decrease your detection performance, particularly when we start talking about falling snow flakes or raindrops. Your LiDAR readings will be including ghost objects, or it will lead to some misdetections. You will for sure also face challenges related to control side of the vehicle, particularly when we have the slippery road surfaces. The friction on the road surface will change a lot, so that we have to design a controller that will take into account this fact about the road surface. Even if you claim that you have a robust system, the testing is difficult. How can we validate your solution and make sure that it follows some standards, right? Those are the real challenges that we can use. And here I just show you one simple example. That is a data coming from KIDI dataset. It's a publicly available dataset. On the left, you see how LiDAR point cloud looks like in clean day, and on the right, you see the corresponding camera image data. It looks fine. You can, of course, there are some challenges, computer vision challenges, but still you can use off-the-shelf perception algorithms to handle these cases. But the problem starts when you have bad weather conditions. You may observe this water fake sub-point clouds in your LiDAR point cloud space, or you may have this kind of blurry images. From my point of view, it's also hard for human perception to say how many vehicles there are or whether there is anything approaching or colliding. So those sensors are negatively impacted by these challenging weather conditions. ROADVIEW is addressing those weather-related challenges by developing robust and cost-efficient embedded in vehicle perception and weather-aware decision-making system. So we are addressing both parts, not only perception, but also we are willing to make the decision-making system more aware of the weather conditions for connected and automated vehicles with enhanced performance under harsh weather conditions. So in the context of ROADVIEW, we are willing to have more improved perception system where we are taking into account the slipperiness of the road surface. We are paying more attention to the VRUs and, of course, the visibility coming from this degraded sensor performance. And we are willing to have a decision-making system which is more weather-aware, so that the vehicle can have better performance under bad conditions. And the testing and validation, whenever we provide a solution as a ROADVIEW innovation, we are willing to have hardware in the loop, software in the loop test to make sure that they are deployable before you go to demo sites. ROADVIEW indeed aims at closing this important research gap and willing to collect a bunch of data from different ODDs covering bad conditions in highway scenarios or urban environment and so on to reach the TRL 7, which is a challenge itself. ROADVIEW is coming with a bunch of innovations. I would like to go through them one by one. So the first innovation is the early sensor noise filtering part, where we do not want to pass these noisy sensor readings directly to the downstream perception tasks. Instead, we are developing an AI-based cleaning method, which is cleaning the noisy readings from the sensor and then passing the clean version directly to the perception algorithms. We are also introducing a new concept. Well, not that new. The concept itself is known, but it's not that much applied to this subject. So we are willing to apply a data readiness level to the sensor data. So whenever we say it's cleaned, how much it's cleaned. Whenever we say you have new sensor raw readings, how bad it is. So is there any metric that we can use to come up with a generic solution? So just like the TRL level, we are willing to have a readiness level concept for the data itself, because everything is based on AI, and AI is a data hungry method, and this is a must at some point that we have to do. So adaptive sensor fusion is another solution that ROADVIEW is introducing, because at some point those vehicles coming with a bunch of different sensors, like maybe multiple LiDARs, multiple cameras, but maybe at some point some of them are redundant. Can we find a solution so that the vehicle can autonomously select, figure out those redundancies in the sensor ring and come up with an optimal cost-effective sensor setup for different weather types? So that's a very interesting research question for us. We are willing to have this V2X communication in loop to have collaborative perception so that we can have a better perception of the environment. Because we know that there are many challenges, even if you exclude the weather concept itself, like occlusion and so on. So this V2X will boost the perception part definitely. So we are going to have different sensors in the infrastructure, and we'll communicate this thing with the vehicle as well. We are also introducing the new concept called weather-aware decision making, where the vehicle controller, let's say speed controller, will definitely take the visible area and the disciplines of the road surface into account when it is making decisions, critical decisions. Another solution is about, of course, the AI itself. So far, most of those AI-based solutions are black box. So yes, they are working, they are robust, but we do not know how much reliable they are or how transparent they are. So our ultimate aim is to have more grayish boxes instead of those black boxes when it comes to safety critical applications like autonomous driving. Last but not least, before we deploy these solutions to the vehicles, we are willing to have weather capable X-in-the-loop testing environment where the software components, hardware components, and the vehicle itself will go to this loop and to validate your solutions and sensor rings. All right, so those are the innovations, and what we do is we have 3 pillars to achieve those. In the first pillar, we have synthetic data, where we collect data from simulators. Then we have more control environment, where we introduce a certain amount of noise to the environment, like rains and so on. And then we collect data from real world, which all goes to the perception algorithms plus the controller. Then we just pass everything to the validation phase, X-in-the-loop test, before deploying. So I'm going to give you a brief overview about our current solutions. For the pillar 1, we have implemented a simulator where you can actually change the parameters. I call it a parametric simulator, where you just play with tune the parameters and change the amount of noise. For instance, snow in the environment, you can change the snow in some particular area as well. So it's very useful when it comes to collecting data for free in the simulators. And for that, we are creating various digital twins. For instance, the one from Lapland region, it's in the Arctic Circle. And we are also creating different digital twins from different places in Europe, where the overall ROADVIEW system will be tested, like in Turkey, Germany, Finland as well. In the pillar 2, we are having rain tunnels. For instance, this is showing one experiment that we have done in Germany, where we are using sprinklers to inject different amount of rain to the environment. And we have a sensor ring, which is having LiDAR, 4D radar, cameras, and so on. Then we collect how much noise we have in the system. Because you have a control environment, you can measure the amount of noise in a more reliable manner. And this information is then used to create mathematical model of these noise factors. So can I mathematically describe those following snowflakes or raindrops If so, can I boost my simulator accordingly? And in the real world data, we have different vehicles, but here, for the sake of simplicity, I just show one where we have a LiDAR camera and thermal camera and also small sensor here placed in the front of the vehicle so that we can measure the slipperiness of the road surface. This is how the sensor fusion looks like. We have camera on top of that. We have the LiDAR readings. We have the thermal camera here. And this Vasala sensor is giving you this blackish stripe, which is extremely useful when it comes to measuring the slipperiness of the road surface. We also implemented a method which is taking, for instance, snowy LiDAR point cloud like that, shown on the top, cleans these snowy particles directly in the real LiDAR sensor so that this information be passed to the fusion method or other downstream tasks. Those are just like small short videos or animations showing you the solutions that we have achieved in the very first year of the project. In a nutshell, I can say that ROADVIEW focuses on solving weather-related perception and control challenges, and we are willing to have the best bad weather in this case. We are creating our test environment with the simulator control facilities and real-world data, and we are providing vehicle-agnostic solutions. It is because we have different vehicles, trucks, the passenger vehicle, and a small van. And we are also having this weather-aware X-in-the-loop system where we validate our solutions before the deployment. So all in all, it all goes to the conclusion saying that ROADVIEW is willing to enable vehicles going from more autonomous to semi-autonomous. With that, I'm done. I don't know how much time we have left. I think we're doing good with timing. Just a short note here before we switch to Q&A session. Please, I provide you a QR code here. Please scan that one if you want to give any feedback about the overall content of this webinar, because we are willing to have a follow-up sessions. If you are willing to feedback, please just do so by following this link. With that, I'm done. We can now go to Q&A session. Now I will kindly ask each moderator, or Matiwat, Umut, and Graham, please review the questions regarding following to your session, and then pose them, because we have like almost 20 minutes left. I think we can go through those questions. There are already some, as far as I see. Maybe we can start with Matiwat if there is any relevant question.
I actually don't see any question in the Q&A yet.
Okay.
So I guess there's nothing. There was a comment related to the presentation, whether about one of your use case, Edward, that is from Oscar, I think, at Hamza University. He just commented that isn't one of the disadvantages of 5G new radio the inability to deal with the use case such as electronic emergency brake lights, since it is suitable for periodic message rather than an on-demand message. But I asked him to clarify a bit in the chat, but I think it's more like a comment. It's not the real questions. Otherwise, there's nothing yet, but I can ask one thing. You mentioned a lot about digital infrastructure in your presentation. My question would be, do you think that this infrastructure, or especially digital infrastructure, is a long-term solution for automated vehicle to be tested, or do you think this is just a intermediate solutions before we can have standalone automated vehicles without much support from the infrastructure?
Yeah, I guess I'll comment on the comment and say that the protocol that's in use in the electronic emergency brake light particular use case or experiment is SideLink. So this is a V2V technology. So they're not cyclic, but on event messages, and so they can respond. to this type of situation that I described. And then as far as the infrastructure goes, I think the point I was trying to make is that we have always attempted to put structure in the world around us, whether it's in a factory for assembly or on the road when we're driving or in our homes, that represents really embedded, pre-processed information. I think that initially this project, which will be stood up now by IEEE and SAE, they will create an open database for safety issues relative to AVs, ordinary vehicles that are not automated, and the infrastructure, together with solutions and data that suggests just how well the solution works. So that resource is an attempt to do something to organically build consensus. I might mention that I held a meeting in the Midwest 2 weeks ago as a result of the White House announced a national standards strategy for critical and emerging technologies. So among other things, that included robotic cars or automated driving, and the problem there that was discussed with the executives from Google, Apple, the car industry, Intel, was that these standards tend to take a very long time. So in the case of AV technologies, they view this as critical, meaning a security and safety question. They also view it as emerging, which means we don't have enough experience to write standards. So I want to mention that problem so that everyone is aware of it. It's important that the demographic of standards development change from its pattern in the past, and that we have an inclusive approach which has integrity for building. Thank you.
Thank you. Yes, since there's no question specifically here, I think we can just go around and pass along to other speakers.
I think I see a question for Aaron specifically in the Q&A session. So if you can describe how ROADVIEW is creating physics-based digital twins, specifically how the snow on the ground is modeled, the density, particular size, freeze, thaw effects, etc. Can you see the question, Aaron?
Yeah, I do. So those digital twins, we are not using very complicated math behind that. So those are the early implementations, and there is, I assume, a publication which is coming very soon explaining this thing, which is done by one of the groups from Finland, Lapland University of Applied Sciences. So I can simply pass it to you, but I'm not aware of those technical details when it comes to modeling using this particle size and freeze thaw effect and so on. So maybe I can guide you, Ryan, to those right people to get more details.
Super, thanks, Aaron.
Yep.
All right, there's also a question from Oscar. So perhaps, Aaron, you can read that out.
Yeah. Which V2X I think this is what Matti was referring to. Which V2X technologies are you considering? Things like collective perception are proven to be challenging for cellular V2X. Is this assessment with the context of your project? No, this was not the same question. I think Matti was referring to something else. I'm now looking for my partners from the CRF because this goes to outside my expertise. Or Umut, do you think we have this knowledge already?
I saw the question already and looked at some of the slides prepared. So right now, I think the challenge is regarding the availability of the utmost technology, let's say 4G. So the modules that we have in ROADVIEW plans to use the public network, but we plan to like generate the messages so that it can also be transmitted using 2G when the signal is so lower, let's say. But this is an extremely important point, I guess, and we should share it with the colleagues that are responsible for the V2X. Hope this helps. Maybe we could go on with Graham and answer some questions, and then we can go with me and answer some more.
Yeah, can do remote. Again, I'm scanning down the Q&A list. I don't think there's anything at the moment specific for Ryan Lam. I did have a question for you, Ryan, if that is okay. First and foremost, well done for the presentation. I know we had a bit of a dodgy connection, so well done for persevering. So my question for you, Ryan, was for your the two use cases that you had selected, and I'm assuming you have a much larger portfolio of projects. There seems to be quite a high reliance on LiDAR, particularly for localization. Did you care to maybe comment on that?
Yeah, sure. So typically it's a fusion of sensors. The hay bale activity was a fusion of LiDAR and cameras, and then the slope detection utilizes also LiDAR cameras, and I believe radar is involved in that one as well. So, you know, typically, yes, there is a dependence on LiDAR like it is with most automated vehicle systems. However, there's a backup, or not a backup, but an augmented sensing modality there. In the off-road context, I did talk a little bit about material classification. And one of the reasons why LiDAR is quite negative in the defense setting is because it's actively emitting. And so there's a big push within defense use cases for EO-based or passive sensing approaches to doing the modality. And so some of the material classification work can really take cues out of spectral signatures and texture and things like that in order to pull it forward. You know, radar is showing some promise for looking sub-snowpack. We've done some research in that area. It's not conclusive yet, but it is showing some potential benefits. Again, this would be different from a forward-looking radar, more canted downward direction, things like that. But yeah, off-road mobility has some unique challenges, and to the extent that it can leverage automotive-grade sensors, that's great, but we haven't found the ultimate solution for all use cases yet with single modalities.
And maybe a follow-up question as well, Ryan, with respect to maybe the agri-tech, actually for both, I guess. What about maintenance and looking after the sensors, particularly for use cases, applications which are being deployed in a real life setting? Is there considerations around that, or advice that you provide your industry partners in terms of maintenance overall? I think I spotted, for example, a house the LiDAR on one of your rigs, which is off-the-shelf LiDAR.
So some of the challenges there, and I think you guys are experiencing that on ROADVIEW also, is if the temperatures are quite extreme, they have a tendency not to function at the far range parts of the operating range of the temperatures, and so either heating or something like that, but also some of the lens occlusions on cameras. So we've experimented with a variety of different techniques, either using air curtains or something like that, windshield wipers, or some way to clean the lens off as you're in operation. In some cases, those techniques that you put in place can actually have a negative impact on your perception algorithms, so they need to be filtered appropriately and things of that nature. So the Mark I eyeball that blinks on a regular basis tends to clean itself, and so there's some techniques that you can apply for different sensing modalities as well. But it does become a problem, especially when you're in motion and you've got a lot of blowing snow that could potentially accumulate on the sensing head itself.
Yeah, thank you. And maybe Aaron, for you to take note, I think Ryan may have given us an idea for ROADVIEW 2.0. I think
Exactly.
off planet,
Exactly.
I believe that was the suggestion.
Exactly. Wonderful, Ryan. Thanks. Then we continue with Umut, because there are a bunch of questions to Adastec, to Dr. Ali.
Yes. So I guess it was asked several times. What about the Stavanger deployments? Would you like to elaborate on that?
Yeah, the Stavanger deployment, as I say, it's connected to existing network of transit, so with paid passengers, and currently still operational. So anybody who pays like the tickets can try autonomous vehicle over there. So I already mentioned some of the challenges we had, especially the there's a lot of jaywalking involved. So that's why we are trying to handle that. Like also, you need to do some automated horn, since sometimes they don't go away, and then it forces you to drive a little bit more aggressively to be able to conclude your route in time. At the beginning, because of that, we were able to finish our route in 25 minutes. Now we go down to 17 minutes, since we are able to handle those things a little bit better. And also, because of the parked cars, we need to go to the unallowed side of the route. So currently we are overtaking the parked vehicles, which is something new. So basically that route will stay as a more trial of the new things, and then we will do the maybe untouched aerial deployments to elsewhere. So currently we are planning, as I say, another route, and actively collecting every week. One day we are in shadow mode, collecting data from that route to test our systems, since it's a little bit high speed. So it'll go up to 5 kilometers per hour. There's a tunnel, and so that's why. And also, especially the tunnel is very important, so you shouldn't create any problems in that tunnel. So that's why we are currently collecting data, and we hope we will extend our deployments in the Nordic region. Since we have a good partner, we have a good partner also helping us to get the license and provide shared data to governments. So we will be continuing the deployments.
Sounds great. Edward, I guess you have a follow-up. Please go on.
Yeah, so this is sort of tangential, but I was I was listening to Aaron's description of ROADVIEW, and I understand, having lived in at least 5 countries in Europe, that the regulatory landscape is different. In Sweden, the yearly inspections of the vehicle were, sense that they tried to punch holes in the body of the car to see if there was any rust damage and send you off. They tested braking. But in the US, NHTSA's regulatory role involves investigations on issue report and so on. But all of the tests that are conducted on vehicles, current vehicles, are on perfect vehicles under perfect conditions. So I'm curious to know whether ROADVIEW is seeing an evolution of those regulatory frameworks in Europe, where they would actually be prepared to assess a vehicle's performance in snow, for example.
Yeah, this is one of our wish lists to do. This is in our to-do list at least. We are willing to give our feedback to those decision makers when it comes to standards, or what's the expected perception performance when it comes to snowy case. Doesn't have to be harsh snow. We have already defined different levels of rain, snow, and fog, and we are willing. We will also introduce different KPIs, like metrics, to validate the performance of your system. Then we'll propose this thing as a kind of learned lessons. Of course, it's all up to the decision makers to consider that, but we are willing to go one step further. This is not just something that we will experiment and then leave it there. Definitely not. Very good point.
So just as a follow-up, I mentioned the OES that was developed at NIST to give the measurement science for the ODD.
Right.
And I'm curious how the ODD is evolving in Europe. So I'm assuming there's no consensus on one framework for creating ODDs, but are the people working in the research or in government interested in how to measure light, medium rain, measure
Right.
lighting conditions?
Right.
Is there interest in this?
I'm not aware of any kind of consensus like that, but maybe I can ask my team here if there is anyone aware of such groups.
I mean,
could
there
briefly
is.
comment.
Yeah, Graham, go
Yeah.
ahead.
Sorry, yeah, I could briefly comment, Edward. Certainly from a UK point of view, so the British Standards Institute, BSI, NPL, National Physical Laboratory, working with the Met Office. So there's quite a lot of work being commissioned by the UK government through NPL, working with the Met Office. So the Met Office look after our weather, or does all meteorology and the weather predictions, etc. In terms of trying to quantify the different types of weather, shall we say? So what is light rain all the way through to torrential rain. Typically looking at historical data as well. What do we experience in the UK to try and determine what are these vehicles, sensors, systems will need to be able to deal with. So they published a report on rain, and rain by different areas of the UK probably about 5 years ago. I believe they've just published another report on snow only a couple of months ago. So definitely there's an interest in this area, but it's an evolving area. I think we're still trying to understand, when we say extreme, what do we actually mean?
Yeah, I think that personally this is going to be critical, because the vehicles that might be certified in the US will have to cease or downgrade the automation based on the ODD. So if it departs from its ODD, if the ODD includes restrictions on weather or lighting conditions, it will have to shut down the automation. And the question is, it has derived measurements from the sensor array that the vehicle has. So it has an internal version of rain, and then there is that real version of rain. And it seems to me that that's why communication is going to be critical, and the vehicle won't be able to do all these calculations on their own. Thank you, Graham.
Thank you.
Hey, Edward, one thing that I can add there is there's a report that I'm writing with Siddhartha Kasky from WMG as part of ISO TC204 WG14 that's talking about the technical considerations that are necessary for defining an ODD relative to deviation of boundary conditions. So just that condition that you're talking about there of you're going to go outside of an ODD boundary, that has implications on how you actually define that ODD. So hopefully that report, I think it's going to come out in the next 6 to 9 months. So that might help some of the industry discussion on that.
That's a great comment, Ryan. I mean, the obvious restriction that it degrade automation when it exits its ODD sounds great, but it has to know whether it's departed its ODD. And that means it has to measure something. That's great. Thanks, Ryan.
So adding up to that, there is an ISO standard that was published very recently regarding the definition of ODDs. It's not, of course, a silver bullet, but it's a good step towards Europe's, let's say, efforts towards a common ODD definition. I think we have like a minute or not. I don't know.
No, we are just running out of time. Actually, time
Okay.
is over.
Maybe if I can ask one last question to Dr.
Yes.
Ali Peker. So I've seen some safety and security questions. I'm just gonna fuse them and ask you, what do you think the challenges regarding safety and security on blocking your road to becoming profitable? Do you see the break-even point in the near future, or is there a major blockage?
I think that the advantage of doing this globally is that if you hit a problem in one location, then you can solve in the other location. So, but what we do is that we take a holistic approach on the safety and try to put all of them in our roadmap. So I think there are around more than 20 different standards that we need to follow. And we already defined them in our roadway. Of course, some of them requires changes in the vehicle, some of them requires changes in the hardware, but we are keeping a holistic approach. So the product is safe. The driverless movement is a side outcome of it for us. So in our part, is road to profitability is a little bit shorter compared to small vehicles, taxis and things like that, since they spend a lot of money. So, in our case, our solution makes sense. It has a clear return on investment. So if you're able to do the bus driverless, you save from energy and labor, and that the bus pay itself in 2-3 years. So it solves a real problem. Since there's not enough drivers, it solves a real problem since you need public transit in many places. So we don't see far away for profitability. So operating around 150 buses with our technology will convert our company to profitability. It's
Very
not far away.
Very impressive.
So there was another question. It was from my side indeed. I was wondering about your sensor fusion and the radar technology that you are using. Was it a 4D radar, 2D radar, or what kind of fusion did you use?
For us?
Yes.
For us, we basically our approach was similar to what you were planning in ROADVIEW. So we had some filtering in all sensors, and of course we have a cleaning system. And so we don't use 4D radars. There's a lot of them we have seen, but we couldn't get a automotive grade sample in our hands. Since I think that the problem with the buses or in general commercial vehicles is that everybody would like to sell their products to automotive since there's huge numbers, but they don't have real use cases. So we have the real use cases, but we need to wait for others to get the B samples, C samples, and then we can have the product. So we are using the things that are already available, like standard radar, Auster lidars, and cameras, RGB cameras, and thermal cameras. And of course, we are using the map itself as a sensor to use it as a empty version of the world. So it helps a lot. So we fuse them all, including the data. So my PhD is basically on fusing existing data as a sensor, like maps or communication. So we are fusing them all to get the results to be able to cope with these conditions. Our problem is difficult since we need to operate all the time. But our problem is a little bit easier since we know the route well beforehand. So we can do a lot of, we can use a lot of existing information. So we have a baseline. But of course, it's a big vehicle. You should localize better since you need to be very precisely docked. You should deploy the ramp, and then your load is changing. Control is difficult. You cannot apply harsh brakes. People are standing. So there's more difficult problems, but classical autonomy problems in the perception and prediction is a little bit easier.
Thank you. We're almost done. There are two more questions. One is about, like Yusuf was saying, almost all companies and universities look like working with cars or buses. Are there any of those using mobile robots other than Ryan? I think there are some groups in the US and Europe collecting data with small mobile robots. I can share the links later. At least I know one group from Czech Republic. They have already released data collected with mobile robots. So, but of course, investments are more when you have vehicles. So that's, I think, one of the reasons why you have so many data sets collected with real vehicles. The very last question is, are there opportunities to share collected OEM data for Scotland, UK, open data which meetings national privacy regulations. There are some public data sets available from Canada, from Europe as well. I don't know which OEM you are specifically asking or referring to, but at least for the ROADVIEW, we are also willing to release some labeled data, not only raw data itself, which is cheaper, but when it comes to annotation and having diversity in your data set, it's a challenge itself. So we are also willing to make a public release of some annotated part of the data. I think we visited all the questions to my best knowledge. Otherwise, please get back to us again. With that, we are done. I would like to especially thank to Mario, who was organizing this webinar. Thank you very much, Mario. You did a wonderful job by putting all these people together. We reached more than 50. I think it was productive. Thank you very much, speakers. You did an amazing job. I think from the questions, we understand that you are the right people. Thank you very much. We'll keep you in the loop with the development of ROADVIEW. With that, we are done. Thank you very much. Hope to see you in the next webinar later. Thank you.
Thanks a lot. See you guys.
Thank you. Bye-bye.
Thanks, all.
Bye.
Take care.